Hi, I'm here today and I'm going to give a presentation on aerodynamics in a turn. But before we do that, we'll have to talk about aerodynamics in a hover, aerodynamics in forward flight, and the elements that are related. So as you can see, in our helicopter, when we're hovering, no wind situation, we have weight and drag equal to lift and thrust. Let's talk about lift and thrust. Lift and thrust is created by the main rotor system. Weight, obviously, is the weight of the helicopter with gravity. Pulling it down, and drag as well are from the lifting surfaces, rotor blades, etc. Are actually creating, in this case, the downward force. So they're all even in a hover and a no-wind situation. Let's talk a little bit more specifically about drag. There's three different types of drag: parasite, induced, and profile. Parasite drag comes from particularly the non-lifting surfaces, like your skids, rotor mass, things of that nature. Induced drag. Let's talk about induced drag. Induced drag is created from the rotor blades, particularly in our helicopter. That's where the high pressure from below meets the low pressure above at the trailing edge of the wing, and this creates the vortices that actually trail behind the helicopter. Profile drag is further broken down into two types of drag: skin and form. Skin drag. This is the type of drag that you get from having uneven skin surface, rivets, bugs, that kind of thing. Form drag. Form drag is kind of hard to explain, so I'm going to show a diagram in just a second, but form drag is basically turbulent air that's created by the separation of airflow from the surface of a structure. So I have a diagram that I'd just like to show out of the helicopter pilot textbook of form drag. This is a good demonstration, and I thought this was worth showing. As you can see, the airfoil, or in this case the rotor blade, pretty smoothly, the air flows pretty smoothly over it and underneath it, but something that hangs down creates definitely a large amount of turbulence behind it, thus creating a fair amount of drag. Now that we've talked about the aerodynamics in a hover, in our helicopter, I'd like to talk about some aerodynamics in forward flight. Now in forward flight, lift, which vertical lift in this case would be here, actually splits, and it splits into vertical lift and horizontal lift. As you can see here, you need some horizontal lift to actually move the helicopter forward, which is the tilting of the disc. So the total or sum of the vertical lift, the horizontal lift, is the total resultant lift. Same with the weight and drag as in the former hover demonstration we talked about. Drag is acting opposite of thrust. Weight is acting downward, opposite of the vertical lift. And the two together is your resultant load in this case. Now let's move on to banking our helicopter, or turning our helicopter. And this is, I term this medium bank. This is about a 30-degree bank per textbook. So what I'm trying to show here is, once again, that the vertical component splits into two, the horizontal and vertical component. And the two add up to be your resultant lift. This is a good time to probably talk a little bit about Newton's third law of motion. And Newton's third law of motion says for every action there is an equal and opposite reaction. So how does a helicopter turn? Well, the rotor disc actually tilts, but centrifugal force, or centripetal, yes, force, is the force that actually turns the helicopter. So this opposite reaction, this Newton's third law of motion that I'm talking about, is created centrifugal force. So why is that important? Well, centrifugal force and weight, as you can see here, total up to equal your resultant load. And we'll see how that's important in just a minute. Now I'm going to move on to a steep bank diagram here that I've drawn to kind of show you, which will move into load factor. I'm going to show you actually that here in a moment. So the same thing here. As you can see, these are vectors. These are what we call vectors. And the vertical component, again, splits into two, horizontal and vertical, to equal the resultant lift. And same as we talked about before, the centrifugal force and weight equal the resultant load. Now as you can see, the steeper your bank, the more horizontal component of lift you'll need, and the more centrifugal force is created. So the sum of these two forces, centrifugal force and weight, or the resultant load. So why is that important? So as you can see the difference here, that's important because load factor. Airplanes, helicopters, they have a load factor limit. Let's first of all look at the definition of load factor from the Rotorcraft Flying Handbook. It's the ratio of the load supported by the main rotor system to the actual weight of the helicopter, i.e. aerodynamic loads. So these aerodynamic loads that we're talking about is basically this: the centrifugal force, the weight of the helicopter, totaled together is the aerodynamic loads, i.e. or load factor. And like I said, this is important because all aircraft have a load factor limit, usually in your POH. So it's important to know that when you increase your bank into a steep bank, your load factor is going to increase. I have drawn here next a load factor chart. And what I'd like you to take from this is basically that, like in our hover, in unaccelerated level flight, our load factor is about 1. This here is our load factor number. This here is our angle of bank. So about at 10 degrees, it's about 1, a little over 1. And about 30, it's still about 1. Now, when we increase our angle of bank to 60 degrees, our load factor increases to 2. So what that means is that at a 60-degree angle of bank, our helicopter is supporting twice its own weight due to, i.e., aerodynamical loads. So it's important to keep in mind in turning flight that as your angle of bank increases, your load factor increases as well. So today we've talked about the aerodynamics in hovering flight, in forward flight, and in turning flight. I hope you've learned something from my presentation. Thank you.